should take it slow.
Okay, hello everyone, and today we'll be doing partial fractions. So, in other words, how to separate fractions with factors in the denominator. So, first of all, we're gonna look at proper fractions with unrepeated linear factors. So, firstly, we're gonna write this in the general form: p of x over ax plus b into cx plus d is equal to capital A over ax plus b plus capital B over cx plus d. Now, basically what we do with partial fractions is it allows us to separate a function such that there's only one term in each numerator. So this function could have several terms, and it makes sure there is only one term for each numerator of the separated pieces. So let's go ahead and start with an example: 5x plus 7 over x plus 1 into x plus 2. Now, according to the general form we had earlier, we'll rewrite this as capital A, over x plus 1 plus capital B over x plus 2. Now, what we'll do from here, we will multiply everything by this full function down here. These two factors down here, we multiply everything by them. So obviously, if we multiply this whole term, by this, we will just end up with the numerator alone because it's gonna cancel out. So we'll have 5x plus 7 equal to, and now if we multiply this whole thing by x plus 1 x plus 2, x plus 1 will cancel, leaving a times x plus 2, and then similarly for this one, x plus 2 will cancel, leaving us b times x plus 1. Now, if you haven't figured out what we're doing here, what we're basically gonna do from here, we're gonna expand this and then line up coefficients. So we're gonna say that 5x plus 7 is equal to ax plus 2a plus bx plus b And now we can go a bit further and say that 5x plus 7 is equal to a plus b all times x. A plus b all times x plus 2a plus b. Now what we can do now is that since we have a plus b as the coefficient of x here and 5 as the coefficient of x here, we can say that 5 is equal to a plus b. And we can also say that 7 is equal to 2a plus b, because again we're lining up constants with constants. And from here we can actually solve this in a simultaneous way. As you can see, we'll have a simultaneous equation, and so we can go ahead and solve it like a simultaneous. I will say that b, let b equal 5 minus a, and so we can say that 7 is equal to 2a plus 5 minus a, and we can say that 7 minus 5 is equal to a, therefore a equals 2. We can go ahead and say that a equals 2. It's simultaneous. Now what we can also, after that now, we can put 2. Let me write this a bit better. A equals 2. Now we can put 2 in one of these equations and we can get now 5 minus 2 equals b. So now from that we know that b is 3. Now that we know that a is 2 and b is 3, we're going to rewrite what we had before. 5 x plus 7 over x plus 1 into x plus 2 and we're gonna say now it's equal to 2 over x plus 1 plus 3 over x plus 2. So in other words, that's how you separate a fraction like this into two parts with only one term in the numerator. So this is the basis of it. Now let's look at what would happen if we had a proper fraction with repeated linear factors. So let's say, hold on, so it's supposed to be a multiplication sign. Yes. So what if we had x plus 1 times x plus 2 times x plus 2? So we had 3 linear factors, but one of them was a repeat. We had 2 of it. What would basically happen now is that we would have a, so let's write this squared here to represent both x plus 2's. a into x plus 1, a over x plus 1 plus b over x plus 2 plus c over x plus 2 all squared. So in the case where you repeat the linear factor, you have to write the linear factor by itself under the b term, and then write the linear factor to the power squared third under an c term. And if we had, say, x plus 2 to the 3 here, let's say we had x plus 2 to the 3, we would actually have to continue adding more terms, and we would have to add in now b over x plus 2 to the third. But you can see we just keep adding new terms for the amount of powers. This is how it will look when they repeat a linear factor. Now let's look at what it will look like when there's a unrepeated quadratic factor. So let's say we have an unrepeated quadratic factor such as 4 over x plus 1 into 2x squared plus 1. So of course, this is a quadratic because it's to the squared. So what we'll do here is that firstly we'll have the a over x plus 1, as usual. But now, since the other one is quadratic, what we'll have is cx plus d, or my apologies, bx plus c. So because it's quadratic, we'll have bx plus c all over 2x squared plus 1. So that's what happens when there's a quadratic factor. For all the unrepeated quadratic factors, you would have to put one variable alongside one constant and then another constant. So bx plus c. If we had another quadratic factor, like say x squared plus 2, we would say cx plus d, or rather dx plus e over x squared plus 1 to represent it. Okay, that's the general form if you have the quadratic factor, and of course you would work it out like how we worked on the first example. Now for the final thing we're looking at today is what happens when it's a repeated quadratic factor. Now when it's a repeated quadratic factor, let's write back to what we had before. 4 over x plus 1 into 2x squared plus 1, but this time we'll write 2x squared plus 1 all squared. And what we'll get from this is that we now are going to have to compensate for the repeat quadratic factor by doing the same thing we did with repeat linear factors. We're going to have a upon x plus 1 plus bx plus c into 2x squared, or upon 2x squared plus 1 plus dx plus e all over 2x squared plus 1 all squared. And that's how we compensate for it. Just like how we compensate for the repeated linear factor. Now, of course, you might be wondering what happens when the fraction isn't proper. Now, in the case where you have an improper fraction, you would do simple polynomial division, and after you've divided the polynomials, you will get a whole number and a proper fraction which you can then work with. That's what we all for today. Thanks for watching.
Tell me pretty lies, look me in the face. Tell me that you love me, even if it's fake.